Without a doubt, Rubik's Cube has been the most successful physical puzzle ever invented. But in the last 10 years, the world's most popular puzzle, requiring less physical dexterity and more logical reasoning, is Sudoku. Here's a typical Sudoku puzzle. Part of Sudoku's enduring popularity is that the challenge can be described in a single sentence. Enter the numbers 1 through 9 in such a way that each number appears once in every row, column, and 3x3 box. That's it. Every Sudoku puzzle will have a unique solution, and if the puzzle is well crafted, should be solvable using just pure logic. No guessing should be required. Is Sudoku a mathematical game? Absolutely. And it's not because the grid is filled with numbers. It would be just as mathematical if each square had to be filled with a letter or a color or one of 9 vegetables. What makes Sudoku mathematical is that in order to solve it, you need to think like a mathematician by looking for patterns and using careful logic. I think Sudoku is great mathematical training for kids, and for adults it's a fun way to keep your mind active and sharp. I'm definitely a big fan of this puzzle. Now, before I teach you a good strategy for solving Sudoku, let me say a few words about some of the mathematical questions that pertain to this puzzle. With the Rubik's Cube, we asked how many positions are possible, and what's the fewest number of moves needed to solve them. Let's look at some related questions here, starting with how many different Sudoku puzzles are there? Now, as a warm-up question, let's first count the number of baby Sudoku puzzles, sometimes referred to as shidoku. In shidoku, you must fill out a 4x4 grid with the numbers 1 through 4 in such a way that every number appears in each row, column, and 2x2 box. For example, here's a typical shidoku puzzle. These problems tend to be very easy to solve. For instance, here, once you notice that a 2 has to go here, and a 3 has to go here, then the puzzle pretty much solves itself at that point, resulting in this completed grid. The math question is, how many possible completed grids exist? For starters, look at the box in the top left corner. We know that the number of ways to arrange the numbers 1 through 4 is 4 times 3 times 2 times 1, 4 factorial, equals 24. Once you've chosen the order of these 4 numbers, say like so, there are 2 ways to finish the first row and 2 ways to finish the first column, say like so. And it can be shown that no matter how you've chosen all these numbers, there are exactly 3 ways to fill out the rest of the box. I'll leave it as an exercise for you to show that if you put a 1 in this spot, then there's just 1 way to finish. But if you put a 2 in that spot, then there are 2 ways to finish. Hence, there are exactly 3 ways, 1 plus 2 ways, to finish this puzzle. So, altogether, the number of possible 4x4 shidoku grids is 24 times 2 times 2 times 3, 288 ways to finish the puzzle. So, how about 9x9 Sudoku grids? Using similar symmetry arguments and lots of brute force computing, it was shown in 2006 that there are over 6.67 sextillion possible 9x9 completed Sudoku grids. That's nearly 7 billion trillion possibilities, and it's more than 100 times as large as the number of achievable Rubik's Cube positions. And that's just the number of final answers. The number of initial grids that can lead to these answers is even larger, so there should be no shortage of puzzles anytime soon. Here's a related question. Every Sudoku puzzle is required to have a unique solution. Is it possible to be given 50 numbers and not have a unique solution? How about 60 or 70 numbers? Believe it or not, it's possible to be given 77 of the 81 numbers and still not have a unique solution. Now, how is that possible? Suppose I showed you this much of the puzzle. 77 of the squares have been filled. We know the missing numbers are 2 and 3, yet we don't know if they go like this, 2, 3, 3, 2, or like that, 3, 2, 2, 3. Either way, we have a valid completed grid. Here's a much trickier question that was only resolved recently. What is the smallest number of clues needed to make a Sudoku puzzle uniquely solvable? For example, with no clues, there are more than 6 sextillion ways to complete the Sudoku. It's easy to see that 7 clues isn't enough either. Why? With 7 clues, there has to be at least 2 missing numbers. With 2 missing numbers, you can't possibly have a unique solution, right? Say 2 and 3 were missing. Both of them were missing. Then for any valid solution, we could interchange all the 2's with the 3's and get another valid solution. That's why some hard Sudoku puzzles might have 1 missing number, but it will never be missing 2. So the natural question becomes, what is the smallest number of clues that you can be given and still have a unique solution? There are many examples of puzzles with 17 clues that have a unique solution. Here's one of them. This puzzle has 17 clues, count them, but it only has 1 unique solution. In 2012, it was finally shown, using clever search strategies and lots of computer time, that there is no 16-clue puzzle that leads to a unique solution. But other questions still remain open. For example, did you ever notice that practically every crossword puzzle is rotationally symmetric? That means that if you rotate the puzzle 180 degrees, then the black squares are still in the same positions. The same is true with Sudoku. In most Sudoku puzzles found in books and magazines, it's customary for the starting clues to be placed in a rotationally symmetric way. For example, here's a Sudoku with 18 clues placed in a rotationally symmetric way. Right? If you rotated this board 180 degrees, you'd have numbers in the same spots. The 17-clue puzzle that we saw earlier is not rotationally symmetric, and so far, nobody's been able to find one, so it's still an open question if 18 clues is the minimum. Here's an interesting 18-clue puzzle. It appears in the book Taking Sudoku Seriously by mathematicians Jason Rosenhaus and Laura Tallman. Not only is the puzzle rotationally symmetric, but in the spirit of rotational symmetry, the digits of this puzzle come from the first 18 digits of pi. You gotta love it. There's a 3, 1, 4, 1, 5, 9, 2, 6. It's great, and it's rather pretty to look at. But enough talking about Sudoku. Let's now learn the strategies that will allow us to solve most Sudoku puzzles quickly and easily. Now, I should tell you, by the way, that I used to be pretty terrible at Sudoku until I sought advice from an expert. As luck would have it, one of my very own students, a math major at Harvey Mudd College named Palmer Mebane, was an expert at puzzles. Actually, that's an understatement. Palmer was the 2011 United States Puzzle Champion, and later that year was winner of the World Puzzle Championships. He learned his Sudoku techniques from Thomas Snyder, also known as Dr. Sudoku, who is himself a past U.S. Puzzle Champion and 3-time World Sudoku Champion. I'm very grateful to Palmer and Tom for allowing me to share some of their techniques with you. After learning these techniques, you should be able to do just about any Sudoku puzzle that you come across. Dare I say, you'll find them as easy as pie. To prove my point, let's look at that pie puzzle from earlier. Okay, here it is, just 18 digits. How do we get started? Now, before I go any further, let's make sure that we define all of our terms properly. A Sudoku puzzle is played on a 9x9 grid consisting of 81 squares with some number of initial clues. It has 9 rows, 9 columns, and 9 boxes. The numbers that can potentially go in a square are called the candidates for that square. For example, in our pie puzzle, this square over here, it can't be a 1, 2, 4, 5, 6, or 9. So the candidates for that square are 3, 7, and 8. Although soon enough, we'll see why that square has to be a 3. Now, I used to go about Sudoku all wrong. I would enter the candidate numbers for each square in hopes of finding a square with a single candidate. And some books and websites actually take that approach. But I'm here to tell you that this is the wrong way to start the puzzle. You might want to do this if you get stuck near the end, but you definitely don't want to do this at the beginning of the puzzle. In fact, you want to take the opposite approach. Instead of asking for each square which numbers can go in this square, you want to ask for each number which squares can take this number. Let me illustrate. Let's start by looking at the number that appears most in this grid. That would be the number 3, which appears 4 times in this grid. Next, we'll be able to place some new 3s using a process that I call tic-tac-toe. Now, every Sudoku has 9 rows and 9 columns, but if you focus on the thick lines, it sort of looks like a big tic-tac-toe board, right? You can think of it as having 3 big rows, big row 1, big row 2, big row 3, and 3 big columns, 1, 2, and 3. Now, look for a number that appears twice in the same big row or big column. Okay, so here the number 3 appears twice in the second big column. That's in little column 5 and little column 6. Now let's look at the other little column. That would be column 4. And I ask you, where can the third 3 go in that little column? Now, it can't go in the top box because of this 3. It can't go in the middle box because of that 3. So it must go in the bottom box over in one of these spaces. But there's only one place it can go in that box, so the 3 must go there. So I call this tic-tac-toe. By the way, we call the number that we just entered into the puzzle a hidden single. That's a number that has only one legal square in a row, column, or box. Okay, so the only legal place that a 3 could go in that column was there, so that's what made it a hidden single. The best way to find hidden singles is through the tic-tac-toe process. So let's do it again. This time, notice that the big middle row has 2 3s in it, right here and there. So if we focus on the other row, we do tic-tac-toe. Now hold on a second. The third 3 must be in one of these 2 open spots. But it can't be here because of the 3 below it, so it must go here. Now the third big column has 2 3s in it, so we can do tic-tac-toe again. All right, so let's see. Tic-tac-toe, we have to have a 3 in one of here, one of these 3 spots, but correction, it can't be here because of the other 3. So there are only 2 possible locations for the 3. Now listen to this because it's important. If a number has only 2 possible locations inside a box, then I will write that number real small inside of its 2 possible squares. Let me say that again for emphasis. For most of the puzzle, the only time to write a little number in the puzzle is if that number has only 2 places to go inside a box. Not 3, not 4, 2 places to go. I usually write them in pencil so they can be erased later as needed. All right, let's do another example of this. The third big row has 2 3s in it, right? Here and there. So tic-tac-toe gives us tic-tac-toe, but it can't go there. So it has to be one of these 2 spots, so we pencil them in. Now there's one more tic-tac-toe on the board, but it doesn't use 3s. Do you see it? In the last big column, we have 2 9s. So doing tic-tac-toe with them gives us 2 places where the 9s can go up here, right? Tic-tac-toe can't be here, so it has to be one of those two places. All right, and we mark them like so. By the way, let me say something about pencil marks. You'll notice that I put all the 3s in their upper right corner of the square. And I put all my 9s in the lower right corner of the square. And if you think of a square as having 9 places for numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, I'll always put my pencil marked numbers in the same place just to be consistent. Okay, now there are no more places to perform tic-tac-toe, so it's time to learn a new technique. Now with tic-tac-toe, you needed 2 repeated numbers in the same big row or column. When 2 numbers are not in the same big row and column, then we can sometimes use cross-hatching. So what's that? For example, if you cross-hatch the 3s, the 3 in this column and the 3 in this row, we get that no 3 can appear anywhere in this box except for here. And notice how this 3 eliminates this 3 as a potential candidate, leaving us with this 3 here. It also eliminates this 3 here, so the only place for a 3 in this box would be here. We've now placed every 3 on the grid, and we won't ever have to deal with that number again. If I were doing this on paper, I might put a check mark above that 3 to indicate that I don't have to worry about 3s anymore. Let's look for more places to cross-hatch. Now, when I scan the grid with my eyes, I look for certain structures. I see the top left box has a 2x2 mini box. I see a completed line inside this box, and I see lots of boxes containing right angles. Here's one, there's one, there's one. All of these structures tend to be very helpful. Let's start with this angle. Now, this box will contain 3 unfilled squares in a row and 3 unfilled squares in a column, which is sometimes susceptible to cross-hatching. Notice that this row has a 5, and this column has a 5. So when we cross-hatch, there's only one place the 5 can go, namely here in this square, creating another mini box. As soon as you fill in a new number, you should see what kind of chain reaction it causes. For instance, if we do tic-tac-toe with the 5s, we get that a 5 must be, let's see, tic-tac-toe has to be in one of these 2 squares. And also, because of that 5, we have tic-tac-toe has to be in one of these 2 squares. Ooh, that's actually good news, and I'll say more about that later. Okay, let's go for another angle, another right angle. Here we can plow through the blank spaces of this box, cross-hatching with 1s, right? I got a 1 up here and a 1 over there, so that means a 1 has to go here. Once we have a 1, this creates a chain reaction, right? Another tic-tac-toe, tic-tac, and one of these 2 has to be 1. Okay? Oh, and wait a minute. Let's not forget that it could also cause a chain reaction here. Tic-tac-toe, one of these 2 must be 1 as well. Okay, let's do one more angle. All right, so looking up here. Now, if I look at that 6, it plows through this column fine, but nowhere else. Okay, so there are 3 places the 6 can go in that box, so we don't write anything down with that. On the other hand, the number 2 will cross-hatch very nicely. You see the 2 plows here, the 2 plows there, with 1 place for the 2 right there. Okay? Next, once we get a number, we should do tic-tac-toe. Tic-tac-toe, one of these 2 has to be a 2. Good. And then tic-tac-toe. Well, this seems to leave 3 places for the 2. Now, as it turns out, the 2 can't go over there, but I haven't explained why yet, so I won't pencil anything in here. Okay, I'm done with angles. Now let's explore some mini boxes, starting with this nice little mini box over here. Now, with tic-tac-toe and angles, we needed 2 numbers to make progress. But with mini boxes, you often need just 1 number to make progress. Now, when I plow this white space with this 8, that means we're going to have an 8 in one of these 2 squares. So I'll pencil some 8s in over there. And when I plow this white space with the 1, right, you see the 1 going all the way here, well, that's going to force me to have a 1 in one of these 2 squares, so I'll pencil them in there. Aha! Look what happens. Notice that one of these squares has to be a 1. Thus, no other 1s can appear anywhere in that row, right? Because one of these is going to be a 1. We call this situation a pointing pair. You can think of these 1s as like pointing a ray gun across its row, eliminating all other candidate 1s. In particular, this 1 is no longer a candidate, so now there's only 1 1 left in this box, namely this 1. Okay? So we can write it in. Let's look at another mini box. Okay, here I've got a nice mini box that's waiting for something to happen. Now, when we check out this column, we find a missing 4 and 6, right? 4 and 6 are not in this box. So that means that I can't have 4s or 6s anywhere here. That means that a 4 and 6 must go in here in some order. Now, I don't know which of these is the 4 and which of these is the 6, but I do know that these 2 squares can only contain a 4 or 6 since they can't go anywhere else. So let's write them in. We call this a hidden pair, right? We saw, so these 2 numbers have to be 4 and 6 in some order. No other number would be allowed in there. We saw another hidden pair earlier over here. You see the 5, 9 and the 5, 9? Since these 2 numbers, since 5 can only go in these 2 places and 9 can only go in these 2 places, then they must contain these numbers, 5 and 9, in some order. Okay, let's pause, catch our breath here, and let me ask you, what 6 numbers must occupy these 6 squares? Okay? Say your answer. I want you to give me the answer in increasing order. What are the 6 numbers in these squares? 2, 3, 4, 6, 8, 9. Okay? So, what numbers are missing from here? Say the answer in increasing order. The missing numbers are 1, 5, 7. That means that the numbers in these 3 squares must be 1, 5, and 7 in some order. Now, the 1 can't go here because of that 1, and the 1 can't go here. Why can't the 1 go here? Because of that pointing pair of 1s. It's firing its ray gun at it. So the only legal place for the 1 in this box is here. The other numbers must be 5 and 7 in some order. But because of the 5 here, we're going to have the 5 and 7 here and there. Okay? And this 5, by the way, forces us to have a 5 and a 9. We weren't sure what their order was before, but we know now that these must be 9 and 5 to fit over there. Great. Now let's see, what else do I know? Let's look at the fourth column here, this column here. We have 7 of our 9 numbers. It's only missing which 2 numbers? I've got 1, 2, 3, 4, 5, 6, 7. So we're missing 8 and 9. And because there's a 9 there, those 8 and 9 are going to have to go like that. This opens up the puzzle considerably, and the next few steps of the puzzle are pretty easy. Okay, let's see. Now that we got the 8 and the 9, let's do some tic-tac-toe, right? We have 8, 9 here, 8, 9 here. I'm going to have 8, 9 here, exactly, and because of the 9, they have to be 8 and 9 like that. That leaves for us in this box the remaining 3 numbers, right? We've got 2, 3, 5, 6, 8, 9 in this box. So the missing 3 numbers are 1, 4, and 7. Now because of this one of the ones has to go here. We don't know which one. And then the 4 and 7 are somewhere else. But check this out. We call this situation a pointing triple. 1, 4, and 7, because they're here in some order, they can't be anywhere else in this column. This eliminates all other 1s, 4s, and 7s as candidates for this column. Okay, so if I eliminate 1s, 4s, and 7s from here, I see that this can't be a 1, so a 1 must go there. And this can't be a 4, so the 4 must be there. We call that, by the way, a foregone conclusion. Sorry about that. Okay, that forces the last square up here to be a 6. And what's left? Well, looking at this middle column, the only 2 numbers left in this column have to be 6 and 7 in some order. I'll just pencil in the 6 and 7 in both places. Now let's examine the remaining 2 squares over here. They must contain 2 and 5 in some order. But because of this 5, this square here can't be a 5, so it can only be a 2. Okay? Just like that. So a square that can only take on one value, like a 2 here, is called a naked single. And they become more common as our rows, columns, and boxes start to fill up. Naturally, the other missing number here must be 5. That 5 sets off another chain reaction. We must have a 5 here, right? Tic-tac-toe puts a 5 over here, eliminating the 5 below, so forcing us to have a 5 over there. Okay, I might put a check mark above my 5 because now the 5s are finished. Let's look for another naked single. In the top row, we're missing the digits 8 and 9. But this square can't be a 9, right, because of that 9 down there, so it must be an 8, forcing the 9 to go here, and because now we're left with one place for the 8 would have to go there. That forces the other numbers in this row to be 4 and 6 in some order, and that leads to another hidden pair, right? This is 2, 7, and 2, 7 in some order. Now what? We still haven't explained, there's still parts of our puzzle we haven't explained yet. Let's look at this mini box down over here. Okay, so when I look at this mini box, this 2 clears out that row, and that gives us a nice pointing pair of 2s down below. Now, with this pointing pair of 2s, it fires its ray gun, forcing, notice it's going to eliminate that 2, forcing us to have a 7 here and a 2 there. What next? Well, let's see. We have a bunch of 9s on the board. In fact, we have 7 9s on the board. Maybe we can finish them off. Okay, so with our 9s, we do tic-tac-toe. Can't be there, so it must be there. And 1 to go. Once you have 8 numbers, the 9th is forced. Tic-tac-toe has to be there. Although we've completed more than half the puzzle, some challenges still remain. That's part of what makes Sudoku so addictive, by the way. As you figure out more and more numbers, you feel as if the puzzle should get easier. But that's not always the case. It may be that you've only reached the low-hanging fruit, and the remaining numbers might require a ladder. Now, at some point, tic-tac-toe stops working, and there may not be any crosshatches that jump out at you. The question is, what do you do when you get stuck? Here are my suggestions. Suggestion number 1, walk away and come back to it later. After taking a break, you'll often see things that you missed before. Examine the numbers that are almost finished. But if you're still stuck, let's try these techniques. Scrutinize your rows, columns, and boxes that are almost finished and look for naked singles. Don't forget chain reactions. Anytime you get a new piece of information, see what chain reaction that causes. Or finally, you could use the advanced tools that we'll talk about later in this lecture. Okay, in this puzzle, we've finished off numbers 3, 5, and 9. What's the next best candidate? Well, let's see. We've actually solved 6 of the ones here. And when I look at the penciled in ones, we see that 2 of the boxes have hidden pairs. There's a hidden pair of ones here and a hidden pair of ones there. So there's only one box where we haven't said anything about ones, so let's take a look at that box. Now, when I crosshatch my ones in that box, I go here and there. That leaves a pair of ones possibly over here, but that's a pointing pair, right? Those 2 ones are going to eliminate the 1 from this box, forcing a 1 to go over there. And once I have a 1 over here, then the remaining 2 boxes here are 4 and 7 in some order, okay? Anything left with the ones? I have a pair of ones here, a pair of ones there. They form like a little rectangle. There's nothing I can do with those right now, so I'm going to leave them alone. Let's try another number. Let's say 2. All right, so let's take a look. We got 2, 2, 2. Let's take a look at this box. Now, when I crosshatch my 2s, 2 and 2, oh, that's nice. There's only one place for the 2 over here, okay? And this sets off a nice chain reaction. We've got tick, tack, toe, tick, tack, oh, toe, right? We cross out this 2, we're left with 1 over here, and now the 2s are history. Okay, we've now dealt with our 1s, 2s, and 3s. Let's look at the 4s. I think there's not much that happens with the 4s. All I can say is in this box, then because of that 4, I know I have to have a pair of 4s in here, so I can pencil that in. How about the 6s? There's nothing obvious that happens with the 6s, so let's move on to the 7s. Okay, so 7, 7, 7. Wait a second. I see something interesting here. This 7 in this column, focusing on this box, gives me a pointing pair of 7s after I go through here and I crosshatch the 7 there. That leads to a pointing pair of 7s down there. And now I can do tic-tac-toe, right? With tick-tack, because this gives us the column, toe gives me a 7 right over there. Great. Okay, and let's see, does that give me anything else? That 7, what reaction does that cause? Cross-hatching there. I have to have a 7 in one of these 2 boxes, so I'll pencil those in. Okay, finally, let's see what 8s give us. In this box here, there's 2 places the 8s can go, here or there, so we'll pencil that in. And in this box, let's see, there are 2 places for 8s to go there, so I'll pencil those in. That's nice. And now let's look at this box. Let's see, 8s over here and here. Oh, this is good. I've got a pair of 8s that can go here. Now let's pause for a moment. In this box, we can only have, a 1 can only go in these 2 places. An 8 can only go in these 2 places. Even though a 7 would like to be considered for that place, there's no room for the 7 here, right? These 1s and 8s are claiming those 2. So that means the 7 can't go here and it must go there. This tells us, by the way, looking over here, that the 4, 7 has to be 4, and 7 in that order. And the number missing from this row, because I know this is 1 and 8 in some order, and I've got 2, 6, 9, 7, 3, and 5, this has to be a 4. And now the rest is easy. You might say that the puzzle practically solves itself. And there we have it. We're done. We just finished a puzzle that had only 18 clues using rather simple techniques. Let's recap. In this puzzle, we were able to fill in most of our numbers by judicious use of tic-tac-toe and cross-hatching. These would often lead to hidden singles, numbers that could only find one place to go in a row, column, or box. When a number could only find 2 possible squares in a box, we would lightly pencil in that number in both places. If both of those places were in the same row or column, that's called a pointing pair, and that can sometimes eliminate candidates from the other boxes. And if you find 2 numbers that can only go in the same 2 spots in a box, then they form a hidden pair, and those spots must contain those numbers. We started our puzzle by looking for numbers that appear a lot, since they tend to produce most useful tic-tac-toes, right angles, and mini boxes, and since they tend to produce very useful crosshatches. There was one other structure that I mentioned, but we never got to exploit it. It's called a completed line. A completed line consists of 3 numbers that completely fill a row or column of a box, like in this example. Completed lines let you start a tic-tac-toe with 1 number instead of 2. Look outside the box, think outside the box, and look for numbers that are in the other 2 columns. Now look for any numbers that are not in the box below. So for instance here, I see 8s and 9s in the other 2 columns that aren't in the box that contains the completed line. The number 8 forces us to have one of these 2 squares below as an 8, giving us a pointing pair of 8s in the bottom box. And this forces a pair of 8s in one of the middle box squares. The 9 helps us even more. So this 9 in the top box forces this 9 in the bottom box, giving us this 9 in the middle box, giving us our 9s and subsequently our 8s. When starting a Sudoku puzzle, the first thing I look for are completed lines. Here's a puzzle created by Thomas Snyder. I like Tom's puzzles because they tend to have an artistic quality about them or some hidden joke beneath the surface. He created this puzzle for the Silicon Valley Puzzle Fest. If you look closely, you'll see that most of the clues combine to create SI, the chemical abbreviation for the element silicon. Even the extraneous clues have some meaning, since silicon is the 14th element of the periodic table and has atomic weight 28. I'll let you have the fun of solving this puzzle yourself, but the key to solving it is to exploit the 3 completed lines here. Using the techniques that we know, you can solve most, but not all, of the puzzles that you'll find in newspapers and magazines. But to solve the most difficult Sudoku puzzles, typically labeled as tough, fiendish, or diabolical, we might need a few more tools in our toolbox. I'll now share with you some of my favorite techniques. But to use them, we sometimes need more information than we've written in our puzzle. The method I've been teaching you focuses on numbers that can only go in a small number of squares. When you've reached a position where you're really stuck and you can't make any more progress through tic-tac-toe, cross-hatching, hidden pairs, and naked singles, then it's time to reverse that approach and look for squares that can only take a few numbers. In other words, now, and only now, it may be time to pencil in the candidates for each square. Be especially on the lookout for squares that can only take 2 numbers. The first thing to look for are what's called naked pairs. A naked pair consists of 2 squares in the same row, column, or box that can only take the same 2 numbers. Let's start with an abstract example, then a real one. Here, the squares indicated in this grid cannot be 1, 2, 4, 5, 6, or 8. They can only be 7 or 9. So since we have two squares that can only accept 7 or 9, those squares must be 7 or 9 in some order. That now gives us a pointing pair, which can be used to figure out other squares. For instance, so the 7 in this column has to go there. Here's a real-life example. We've solved most of the puzzle, but now we're stuck. Try as we may, we can't make any more progress using our current techniques. Really, you just have two options here. Either fill in the rest of the pencil marks or take a wild guess. I'll say more about the guessing strategy later, but let's fill in the pencil marks now. Notice, by the way, that there are only 13 squares that need new pencil marks. That's way less than going through every square at the start. Look at the squares that can only take 2 values. Most of them are pointing pairs that we've looked at before, but some have not yet been exploited. Do you see the naked pair? It'll use one of these squares. Hint, it's in this row. Here they are. These 2 squares can only be 6 or 9. As a result, no other 6s or 9s can appear in that row, so we can remove them as candidates. So we erase this 6 and this 6 and this 9, leaving us with a naked single. Now that we know that this square must be 7, this causes a pretty big chain reaction that solves the rest of the puzzle. There's an extension of the naked pair concept called naked triples. A naked triple consists of 3 squares in the same row, column, or box that can only take on 3 values. For example, if these 3 squares can only take on the values 1, 2, or 3, then nothing else in that row can have 1, 2, or 3. In fact, we can reach the same conclusion even if the situation were like this. It's still the case that these 3 squares can only take the values 1, 2, and 3. In fact, even this situation is a naked triple, where we have 3 squares that can take on the values 1, 2, 1, 3, or 2, 3. It's still the case that no other 1s, 2s, or 3s can go in that row. Here's another neat idea, known as X-wing. It goes like this. Suppose the number 5, say, only has 2 places it can go in column A, say here and there. And suppose that in column B, 5 can only go in the same 2 rows, like here. The X-wing rule says that there can't be any 5s in any of these locations. That's pretty cool and powerful. Why is that? The reason is that if the 5 in column A goes here, then it can't go here. So the only place left in column B is here. In other words, if this is a 5, then so is this. On the other hand, by the same reasoning, if the 5 in column A goes here, then the 5 in column B must go there. You see where the name X-wing comes from? Looking at this big X, we're guaranteed to have a pair of 5s on the corners of this rectangle, so 5s can't go anywhere else in these rows. X-wings can be pretty tricky to spot, but when you find them, they tend to simplify the puzzle quite a bit. Now let me show you my favorite advanced solving technique. It's called unique rectangle. It's based on the fact that every Sudoku is required to have a unique solution. This way, the newspaper or book with the Sudoku can print the one solution to the puzzle instead of showing many possibilities. Another reason the solution has to be unique is because otherwise a solution would require you to do some guessing, and all Sudokus are supposed to be solvable without requiring any guessing. When solving the Sudoku, you can sometimes exploit uniqueness. Let me start by showing you an illegal Sudoku situation. Here we have a situation where there are 4 squares that form a rectangle in the same big column that can only take on the same 2 values, here 7 and 8. We call this a forbidden rectangle. Now, what makes this illegal? Similar to the X-wing situation, there are exactly 2 possibilities. If this number is 7, then that forces our rectangle to look like this. Whereas if this number were 8, our rectangle would look like this. The trouble is that these 2 scenarios are perfectly interchangeable. If there's a legal way to finish this Sudoku, then there'd have to be a legal solution using that rectangle. Either way, every row, column, and box will have a 7 and 8, and nothing else will be disturbed. Do you see that? For instance, if this were a legal solution, then if we interchange the 2 7s and the 2 8s, then this would also be a legal solution. So how do we exploit this situation? Suppose when solving a Sudoku, the candidates for these 4 squares look like this. And again, I have to emphasize those 4 squares we're looking at are all in the same big column. 3 of the 4 squares have candidates 7 and 8, while the 4th square of the rectangle can be 7, 8, or 9. I claim that the 4th square has to be 9. Why? If the 4th square is not 9, then all 4 squares would have candidates 7 and 8, giving us a forbidden rectangle, and this would prevent us from having a unique solution. Now, strictly speaking, all Sudoku puzzles are supposed to be solvable by pure logic, and no guessing is required. On the other hand, if you've filled up most of the puzzle and you reach a point where you get stuck, then I sometimes find it easier to try a quick guess and see what happens. I'll typically choose a square that has 2 possible values, and that will cause a big chain reaction. When I do this, I'll circle my guess and put everything else maybe in colored pencil. Typically, one of 2 things will happen. Either the chain reaction will lead to a solution to the puzzle, in which case you're happy, or it will lead to some kind of logical contradiction, like a row that must have 2 5s in it, in which case you know that your initial assumption was wrong. Mathematicians, by the way, call this proof by contradiction. Either way, you're happy. You've either solved the puzzle or at least you've made progress. Here's another puzzle from No Frills Sudoku. It's one of the last puzzles in the book, and it's given a 4-star rating for difficulty. Starting with these 18 clues and using the techniques we've learned, I reached this situation before getting stuck. Even after adding pencil marks, I didn't see any way, any naked pairs or triples that help us, nor do I see any X-wings or unique rectangles. So now might be a good time to try a guess. Just about any square with 2 values should cause a pretty big chain reaction here. Let's look at this square in the middle of the puzzle. It can be a 5 or it can be an 8. And it's not innately obvious which number it should be. As you can verify for yourself, if you guess the number 8, then you reach a contradiction. Consequently, the number in this box has to be 5, and if you put 5 in that square, that leads to a pretty quick solution of the rest of the puzzle. By the way, there are many variations on the Sudoku puzzle, and many of the techniques that we've learned in this lecture will transfer over. My favorite Sudoku variation is Ken-Ken, which combines the logic of Sudoku with some actual reasoning about numbers as well. Similar to Sudoku, every row and column must contain the numbers 1 through 6, and each cage indicates what the numbers add, subtract, multiply, or divide to. Numbers can be repeated in the same cage, but not in the same row or column. Puzzles like Sudoku and Ken-Ken are fun because they rely entirely on logic. In our final lectures, we turn our attention back to games that involve only pure logic and strategy, beginning with perhaps the most famous game of all time.